Morning, Jordan. Well, good morning, everybody. Thanks for coming. All right, we're going to work on molecular orbitals today. And molecular orbitals are the result of the combination of these atomic orbitals that we've been talking about. So let's look at, well, see if I can get this thing to work here. Yeah. This won't work for too much longer. Adobe Flash is going away at the end of the year. We're going to have to find another site that does as good a job of this one as showing the pictures of what the orbitals look like. So we're going to start off with hydrogen, and hydrogen is just 1s1. And when you've got two hydrogens together, we're looking at the combination of two 1s orbitals. Now, as we know, 1s orbital is spherical. And what an orbital is, just to remind you, is just a volume in which we can expect to find two electrons. That's all it is, just a volume of space where we can expect to find two electrons. So that's the s orbital. If you remember what the p orbitals look like, there's 3 of them, and there's going to be 2 electrons in each of these. And they are along the x, y, and z axes. These are the 2 p orbitals that we're looking at here. All right, so let's take a look at the molecular orbitals. And the first one we're going to look at is the combination of two hydrogen atoms to form H and H. That's what we're going to look at, H, H, the HH bond. So the 1s and the 1s, these are the atomic orbitals, which have the shape that I was talking about earlier. And then we're looking at the bonding orbital, or the way that these will bond together. And this is it. This is what a sigma bond looks like between two 1s orbitals. So when we join the 1s orbitals together, these are the 1s orbitals here that we're looking at. When we join them together, we get what's called a bonding situation. And that is the situation where we obviously have a bond between two hydrogen nuclei. So these are the nuclei here and here, that you're seeing. Now, the other possibility, and we don't see this with hydrogen, obviously it's going to have enough electrons, and I'll show you what I mean by that in a second, is we have the possibility of what's called an antibonding situation. And this is a situation where two hydrogens do not join together. In fact, they are against bonding, if you will. Antibonding is what we call it. This is denoted by a star, sigma star. So what we get is this kind of situation with the molecular orbital, where we have the 1s and the 1s, so these are the two hydrogen atoms that are separate. And then when they join together, we've got two possibilities. We've got the sigma 1s, which is the bonding situation I showed you first, and the sigma 1s star, which is the antibonding situation. Now in hydrogen, we're only dealing with one electron each. So the total number of electrons that we need to account for when we're filling up the molecular orbital is only two. 1, 2. So those two electrons go in here and they go into the bonding section down here. So you'll notice that there's no electrons up here in the antibonding at all, because we don't have sufficient electrons to put in there. So we can actually calculate a bond order, and the bond order is going to be the bonding electrons, which is these two electrons in the sigma 1s orbital, and minus the antibonding electrons, which is going to be 0. So it's 2 minus 0 divided by 2, which is 1. And that means we're going to have a single bond between hydrogen and hydrogen, and this is what we expect. So H2 does indeed form a bond, and that's all well and good. Does anybody have any questions so far? I know this stuff is kind of a bit out there, but this is just the nature of bonding. This is what bonding is. So let's say we try He2. Now you've got to remember with H and H together, it was 1s1 and 1s1. So there was just one electron and, oops. It was just one electron and one electron. Now with helium, it's a different story. We've got 2 electrons to deal with. This is 1s2. And what we're trying to investigate here now is the bonding between 2 helium atoms. Now you can see when we do that, we've actually got now 4 electrons to deal with. So we stick 2 in the bottom, that's the bonding. But we also put 2 in the antibonding as well. If we want to look at the bond order of helium, it's going to be 2 minus 2 divided by 2, which is 0. What that tells us is that helium won't bond to another helium. That's all. It's a bond order of 0. And that's what we expect as well. Helium doesn't react with anything. It certainly doesn't react with itself to form He2. And the reason is because those 2 electrons end up in the bonding and the antibonding type orbital over here. So for every bonding orbital, you're going to find a corresponding antibonding orbital. You'll also notice that, well, this is energy up here. I mean, so bonding is lower energy, antibonding is very high energy type situation. It's kind of like a mirror. You can see this here. It's kind of like good and evil, whereas good is also evil as well. So We've got the bonding, we've got the antibonding over here as well. Does anybody have any questions so far? Okay. So we've got two kinds of bonds we're going to talk about. We've got sigma bonds, and I've already shown you an example of that. There's also another kind of bond called a pi bond. So let's take a look. I'll go back to that diagram. Keep the Firefox, here it is. Okay. So what I'm going to show you are the possibilities for combining p orbitals now. And we'll look first of all at the sigma p. Now, if you remember what the p orbitals look like, they're the dumbbell shapes. This one is along, well, they're calling it the z-axis. But the point is that what we're seeing here is a combination of the red lobes with the blue lobes on the outside. And this is the molecular orbital that we get from combination of two p orbitals that are joining end to end. I'm going to show you a couple of other combinations here. So this is what happens when we join them parallel to each other. And this is called a pi bond. So this is different to the previous one. So we're looking at a side-to-side kind of parallel arrangement as opposed to an end-to-end rearrangement that we had, sorry, an end-to-end arrangement that we had over here on the sigma p. All right, so this is end-to-end. And this one's parallel. So this is parallel in the plane as we view it from the front. There's also another possibility, which I'm going to show you here. And you can see it at the back here, but this is the end-to-end arrangement as we're looking at it from another angle. So this is across, they're calling it the y-axis, and it's going back into the page here. But this is also a pi bond as well. All right, so let's look at the antibonding for the sigma p. Now remember the sigma p, the end-to-end one here, that is the bonding situation. Let's look at the antibonding situation here. So you can see that when we try and combine the red lobe with the blue lobe here, we don't get bonding, we get antibonding. So this is very high energy. We can also look at the antibonding situation for the this one here, the pi, what they're calling the pi x, and you can see again it's that combination of the blue and red trying to get those to match, and it just doesn't. This has to be flipped over in order to make it a bonding. This is an antibonding situation. And here's the y, the pi y. You can see that there. Again, this is going into the page, and we're looking at the opposite combination where the lobes don't match, the colors don't match. These colors are called phases, by the way. That's why, and that's what we're seeing there. And sometimes they match and sometimes they don't. All right, so let's look at what we're seeing there. So in the 1s situation, you can see we already talked about that. We've got sigma 1s and we've got sigma 1s star. In the 2s, it's the same situation. We've got sigma 2s and sigma 2s star for our combinations. But when we're looking at the combinations of 2p, we've got three possibilities because we've got three different 2p orbitals. We've got the sigma 2p, we've got the pi 2p, we've got the other pi 2p. And then we've got the corresponding antibonding orbitals here mirroring that in each case. Now, filling these is not incredibly difficult. So what I'm going to do is I'm going to show you how we fill these. By the way, you're never actually going to have to write this out yourself, but I will show you how, but you are going to be required to be able to fill these orbitals. So let's see how this works. So we're going to be looking at O2. So let's have a look at how we would do O2. The first thing we're going to do and I'm going to show you how this is done from the beginning, is we draw the atomic orbital diagram for each separate individual oxygen atoms. And this is before we do anything, okay? Now remember what oxygen is. It's going to be 1s2, it's got 8 electrons, 1s2, 2s2, 2p4. So this is before we join anything together. We'll put in the 8 electrons, so 1s2, 2s2, and then the p orbitals, we do 1, 2, 3, 4. So we obey Hund's rule here, and we make sure that we put in the 4 orbitals, sorry, the 4 electrons into those orbitals one at a time, and then one in the last one there. We'll do the same thing over here for this one. Sorry, let's fill from the bottom. And that's what the separate O orbitals look like. But what we want to investigate here is O2, and that is what happens when we bond these things together. So what we do is we show the molecular orbitals for the 1s, which is going to be a bonding and an anti-bonding situation. So this would be sigma 1s, that's the bonding, and then the sigma star 1s, that's the anti-bonding. We do the same thing for 2s as well. Again, there's only 2 possibilities. We've got the sigma 2s, which is bonding, and the sigma star 2s, which is anti-bonding. All right, so I know that's small, but you can see it over here in the diagram. Does anybody have any questions so far? Now, when we're doing the 2p, and what I'm going to do is I'm going to show this up here where we have a bit more room. We have actually 3 possible bonding combinations. And 3 corresponding anti-bonding combinations. Now the bottom one here is the sigma 2p. And these 2 here are the 2 possible pi 2p situations. So we can have one along the x-axis, one along the y-axis. And that's going to be these 2 here. So when we're filling these, here's how it goes. So we've got a total of 16 electrons. That's 8 times 2 equals 16 electrons. And we put them in and we fill these exactly the same way as we'd fill regular orbitals. So 2 go down the bottom here, another 2 go up here, 2 go in the 2s, another 2 go in the 2s up here. So at this point, we're here in the diagram. Now, when we're filling the 2p, I'm going to show you up here because I have a bit more room. We've still got 8 electrons to put in. So we do 1, 2, 3, 4, 5, 6, 7, 8. So we always obey Hund's rule here. And you can see that we end up getting 2 electrons in this anti-bonding situation up here. Because we always have to put the electrons in one at a time when we have the same energy levels. So after we've done that, then we've got our situation of being able to figure out how the bond order. And this is how we count the number number of bonding electrons and anti-bonding electrons. I'm going to stop here for a second. Does anybody have any issues with how I'm filling the central orbitals here? How I get these electrons in here? Now, don't worry about the diagram. You don't have to be able to. You don't have to be able to replicate the levels, but you do have to be able to fill the levels. Count the electrons and fill the levels. Does anybody have any difficulty with first of all, counting how many electrons they need, and then filling the orbitals from bottom to top? Does anybody have any issues with that at all?
So on the test, just the counting part and filling it in is going to be on it?
Yes.
Okay.
Christina, yeah. So are you okay with that? The filling part? The counting and filling?
Slightly confused, but I think I'll be okay.
Is there a question you have that could help?
No, I don't have one particular question.
It follows, the filling follows the same rules as the atomic orbitals. You know, when we do we always go from the bottom to the top. We only ever put 2 electrons in each orbital. And then when we have orbitals with the same energy, we fill them one at a time first, and then fill them with the other electrons. It's always the Aufbau principle, which is bottom to top, and Hund's rule, which talks about how we handle orbitals of the same energy.
I think it was the center part. Yeah, okay. Those.
Okay, now, are you okay with 16? Are you okay with 16? How I get 16? Okay, good. So we do 1, 2, do you see my cursor, by the way?
Yes.
Okay, good. Now 1, 2, 3, 4, 5, 6, 7, 8. Then we do 9, 10, and then we do 11, 12, 13, 14. We do one at a time first, right? And this is 15 and 16.
Oh, okay. Okay, I get it now. Okay, thank you.
So it's exactly the same. I know that the levels in the middle are complicated, but you fill them the same way as we fill regular atomic orbitals.
Okay.
Now, everything with a star on it is anti-bonding. Everything without a star is bonding. So to count the bond order, we want the bonding electrons minus the anti-bonding electrons. So let's count the bonding electrons first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So anything without a star on it is bonding. Now the anti-bonding, we've got 1, 2, 3, 4, 5, 6. 10 minus 6 divided by 2 is 4 divided by 2, which is 2. So we expect a double bond between 2 oxygen atoms. Does anybody have any questions? Especially about counting bonding and anti-bonding. That's all I want you to be able to do. Can you count bonding? Can you count any anti-bonding? That's it. That's all you need to be able to do. Any questions? Okay. I'll show you in a second what the test questions look like. You'll have a much better appreciation at that point. So one of the other things you'll need to be able to do is identify bonding and anti-bonding combinations of 2s and 2p orbitals, and also to be able to draw those kinds of diagrams. So for 2s and 2p, let's start with the 2s orbitals. We've got the bonding combination. You'll notice I put pluses in here. This is to designate that they're the same phase. If I want to designate opposite phase, what I do is I do a plus in one and a minus in the other. If you've got 2 pluses, then the combination is what you're seeing here. I'll show you this in the diagram. Let's go back to that sigma. Here he is. That's what I showed you earlier. So the 2 1s orbitals, same color, same phase, forming the molecular orbital, and that's what we're seeing in the diagram here. We do opposite phases, we get the anti-bonding. So you can see that there's this opposite way where we don't see the bonding. There you go. That's anti-bonding right there. Does anybody have any questions? 1s, 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 1s. This is bonding, this is antibonding. Any questions? Now this is my, over here, this is my coordinate sphere, x, y, and z. X is the line in the plane, z is the up and down line, and y is the one that comes in and out of the screen. So this is a three-dimensional coordinate plane that we're dealing with here. So if I'm dealing with z, which I'm calling up and down, and we're looking at the combination, this is what a pi bond looks like. So plus and plus, minus and minus, these are two p orbitals. We join them together and we get the bonding pi orbital here with the plus and the plus. Now this is a single bond that we're looking at here. And the electrons in the molecular orbital can be above or below the plane of the join between these two nuclei here. The nuclei are in the center of the coordinate plane. Does anybody have any questions about this? So that's bonding. Now, if we flip it over and we do minus here and plus here, now we've got the opposite phases and they're not going to bond. This is going to be antibonding. This is what the antibonding looks like. So it's the complete opposite. This is along the y-axis, and we see the same deal. This is a pi bond along the y-axis. That's a bonding situation. And then when we flip one of them over, that's the antibonding situation along the y-axis. This is along the x-axis. This is a sigma bond, and you can see the difference. In the pi bonds, it's parallel. It's a parallel bonding where we get both lobes to bond together to form a pi bond. You can see that there. In the px, this is end-to-end bonding, and this is what the sigma bond looks like. Completely different. So that's the bonding, and this is the anti-bonding right here. The antibonding is when we flip one of these over, we have plus trying to interact with minus, and we get the antibond over here. All right, so those are all the possible things. Let's take a look at the test questions, and you'll get a better idea of what you're going to be looking at. Now, I didn't say any of that was particularly easy. It isn't. It's kind of difficult because it requires a bit of visualization. Okay, so let's see where we're at here. Molecular orbital questions. I'll show you exactly what you'd be expected to do here. So MO versus molecular orbital. How many electrons are in bonding orbitals in O2? So for something like that, what I'm expecting you'll be able to do is, again, fill the orbitals. You can have it, you should probably have it on a separate sheet of paper. You can do it on, you'll be able to do it on scrap paper here. And you'll have to come up with how many electrons are in O2. Let's see, here we go. So it's this kind of thing, being able to draw the molecular orbital diagram and then count the bonding electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the answer there would be 10 for that one. Anybody have any questions? You could also be asked here for anti-bonding as well. So be a little bit careful of that. What's the bond order of C2? So for something like that, let me show you how you would do that. All these use the same. All these use the same orbital diagram. So we're going to do C2, and you'll see how this looks. So it's always 1s2. Actually, we'll just do 1s. And now 2s and 2p. Now carbon and C2. So we've got carbon is 1s2, 2s2, 2p2. It's got 6 electrons. And when I fill those, we do 1, 2, 3, 4, 5, and 6. And we do that on both sides. Yeah, I think what I might do for test 4, and I don't think I did it here, is I will include this diagram without the electrons in it. So you won't have to memorize where the levels are, but you will have to know how to fill it. That's probably an additional thing that I can do here to help you out. Okay, can anybody tell me how many electrons in total I'm dealing with? Anybody want to guess? How many electrons do you see in total?
6.
Nope. In total. Each C has 6.
Oh, okay, 12.
12, right. So we've got 2 of them. So 2 times 6 is 12. So now we put in our electrons. We'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in bonding, now remember the bond order is going to be bonding minus antibonding divided by 2. So let's look at bonding. We've got 1, 2, that's on the bottom, 3, 4, 5, 6, 7, 8. So it's going to be 8. And the antibonding, we've got 2 and 4. So that's 8 minus 4 divided by 2, which is going to be 2. So we expect a double bond in C2. Does anybody have any questions? So it'd be 2, would be the bond order. That's what you come up with. And then you need to be able to identify the pictures. So this is a 2pz bonding orbital. So this is multiple choice, but you still have to know your shapes here. So you're looking at 2pz, which means that we're looking for a p orbital along the z-axis. And it has to be bonding. So these are p orbitals along the z-axis, but they're anti-bonding. You can see they go opposite. That's along the y. That would be the answer. So there's pz, pz, and it's bonding. So that would be the answer. That's how you would do that. So it's a little bit easier for you all, really, than it is when people are doing this on a regular test, because I actually make them draw out the diagrams. I don't like it very much, but that's how it's done. I will make life a little bit easier for you by adding in that diagram that I showed you. All right, if I don't do that, you can harass me about it. Does anybody have any questions? Anybody have any questions?
Will it go past like the 2p6?
No.
Okay.
No, I'm only interested in any element up to 10, which is neon, which is 2p6. That's it. You won't go.
Okay,
you won't go further than that. It becomes quite complicated after that. Does anybody have any other questions? Okay, I would recommend that you watch my videos. Excuse me, watch my videos about this too. I think that's helpful. So that you can reinforce. I mean, I like people to watch videos before the class, but I don't know if anybody ever does. All right. Let me take a look at something here. I just want to see how far I was supposed to get today. All right, let's see where we're at in the schedule here. All right, looks like we're actually running a little bit behind, but it's all right. So we're dealing this week, yeah, and Thanksgiving is next week. Okay. Now, phase diagrams. Phase diagrams are actually fairly easy, really. With phase diagrams, there are a number of kinds of questions you'll be expected to answer. And what we're looking at with the phase diagram is a pressure on the y-axis and temperature on the x-axis. And if you look at them, you can see these lines and you can see these S, L, and G. The S, L, and G represent the phases, solid, liquid, gas. And one thing you'll notice is that at low temperature and high pressure, you expect to see a solid. And at low pressure and high temperature, you expect to see gases. And that makes a whole lot of sense. Let me show you what I'm talking about. All right, so let's say we've got a whole bunch of molecules here and we've got a piston, we put pressure on it. You can imagine that if we push these molecules closer together, they're more likely to become a liquid and then a solid. The other thing is if we cool something, we know it's more likely to become a solid as well. So I mean, you look at water, I mean, you cool water, it becomes a solid, you heat it, it becomes a gas. It really is that simple. Now, what we end up with, though, is a situation where we have these lines that differentiate the different phases. So we've got solid, liquid, and gas here. And, in these kinds of situations, you're always given the phase diagram. You never have to come up with it yourself. So let's say you're asked these kinds of questions. What phases are present at 200 degrees and 100 atmospheres? Well, it's pretty easy. You just look at 100 atmospheres. And then you look at 200 degrees Celsius over here, you can see that you'd expect water to be in liquid phase during that point. Anybody have any questions so far? What phases are present at point X? Well, if you've got an X, you hit the X here, it's actually along the liquid gas line. So what you've got along that line would be liquid and gas in equilibrium with each other. So you'd have both liquid and gas, L and G would be the answer. So I don't think that's too difficult either. Does anybody have any questions? The triple point is the point where you've got solid, liquid, and gas all in equilibrium with each other at the same time. And that's the point where each of those lines joins. That's the triple point. I'm not asking you to identify the pressure or temperature at that point, just where it is on the diagram. critical pressure. Well, the critical point, you see this line, it actually doesn't go any further than that. You might think, well, you know, it just continues on. It doesn't. It stops here. This is called the critical point. This is the end of the liquid gas line. Now, this past this point, what it means is that, so if you've got 374 degrees and 218 atmospheres, what's going to happen is if you go to 376 degrees, there's going to be no pressure you can put on this to turn it back into a liquid. It's going to remain a gas. That's the critical point. So if I'm over here at 400 degrees, there's absolutely no pressure I can put on this gas to turn it back into a liquid. That's what makes it the critical point. The critical point, though, is the end of the line. You've got the critical temperature, which is going to be 374 degrees. That's the temperature at that point. And the critical pressure would be 218 atmospheres. Does anybody have any questions? So that's the critical point. So you could be asked either the critical pressure or the critical temperature. All you have to know is that the critical point is the end of the liquid gas line. Okay, the last part. The temperature is held at 25 degrees Celsius. Describe in detail the phase changes that occur as the pressure is increased from 0.0040 atmospheres. So what I do is I look for 25 degrees Celsius on the x-axis. The temperature is going to be held at that, and then it's increased. So it'll be 0.0040, and then it goes up from there. And you can see it starts out as a gas and turns into a liquid. That's all I'm expecting you to be able to see from that. Does anybody have any questions? It's more about the wording than anything else. Anybody got any questions? Okay, let's take a look at what that looks like on the test. Again, these questions are not incredibly difficult, I don't think. Most people do very well on this part. It's pretty intuitive. Let's have a look. Come on. Okay, consider the phase diagram below, and you'll notice it's a different phase diagram, but the same things will apply. It's looking for the critical pressure. Now, the critical pressure would be the end of the liquid gas phase line, which would be here, and it would be pretty close to 10 to the 7th pascals, would be the answer there. So you choose Pascal, 10% of the pascals as the answer. You wouldn't use the temperature because you're asked for the critical pressure. Does anybody have any questions about this one? The pressure closest to the triple point. So you look for the triple point. Triple point is here where I've got the cursor. The pressure closest to that would be 10 to the 6th pascals. Any questions? So for this one here, we're looking at what phases are present at point X. So you find point X here. The pressure, the phases present would be solid and gas. Is anybody having any difficulty with this so far? Okay. What phases are present at 10,000 pascals and 200 Kelvin? 10,000 pascals, that would be 10 to the 4th pascals, and 200 K. And I'm hoping you can see that would be gas. That's where the cursor is. Any questions? Okay. So the temperature is observed to increase slowly from 10 Kelvin at 10 to the 5th pascals. All right, so what we do is we find 10 Kelvin. 10 Kelvin will be down here. And we start at 10 to the 5th pascals. And we're increasing the temperature. That means that the temperature goes this way. All right, so we're starting at 10 K at 10 to the 5th pascals, and we're going to increase the temperature. So we start as solid, we go through liquid, and then it goes to gas. That would be the answer. Starts out as a solid, becomes a liquid, then becomes a gas. So to be that first answer there. Does anybody have any questions? Make sure you understand that. Okay. All right, so, you know, again, the best thing to do is practice those. So let's look at the phases of matter and intermolecular forces here. And the other thing that's going to be important here is to be able to at least somewhat identify line structures. So let me tell you what a line structure looks like. This is a line structure. So with line structures, all we're showing is points that represent carbons, and then the number of, then everything else around it is supposed to be a hydrogen. That's all I really want you to understand about a line structure. If you just see lines like that, I just want you to think, oh, that's just all C's and H's. That's all I want you to see. Don't worry too much about how you know how many hydrogens there are. I mean, I'll tell you now that it's all about how many hydrogens are required to give you 4 bonds on carbon.
Yep.
That's it.
What you doing?
Thomas, do you have a question?
I'm fine.
Thomas, I'm going to mute you. Okay. If you've got other things other than carbons and hydrogens, those also get included here, and you can see this is how we express an OH. So to be the line for the carbons and hydrogens, and then the OH would be off that. So that's all you have to be able to, do, is to be able to say, well, if it's all lines like this and C's and H's, and then when you've got other things, they're just connected straight off the C's and H's. So what we're going to be looking at are the 3 intermolecular forces. So let's look at the, okay, see if I can find this phases of matter animation. Yeah, this is the one. So let's look at states here. So this is what we're looking at with solid. You can see that even in a solid, you've still got some movement, but it's all kind of in one place. It's only if you can get down to 0 Kelvin that all that movement stops, but that's what a solid looks like. You'll notice also the solid doesn't take the shape of its container. So imagine putting a rock into a beaker. You know that when you put that rock into the beaker, it's not going to change its shape and become the shape of the beaker. However, if you put water into a beaker, you know that water will take the shape of the container. Does anybody have any questions so far? That's the distinction I'm trying to get you to see. So let's heat this up, and you can see what happens. So now we're heating that solid that's turned into a liquid. It is indeed taking the shape of the container. But you can see with liquid, most of the molecules are still touching each other. I'll cool it just a little bit more. There's a little bit too much gas there. But there's always going to be a little bit of gas as well floating above the liquid too. But for the most part, all of these liquid molecules are touching each other. Now, if I heat this more, of course, what's going to happen? It's going to turn into a gas. And now you can see the molecules are no longer touching each other and they're filling up the entire container. So that's what I want you to be able to imagine here about the distinction between solid, liquid, and gas. Does anybody have any questions so far? Okay. What we're going to focus on here, though, is that liquid to gas kind of transition. So what I want you to imagine is I told you with liquids that the molecules are all touching each other. So what that means is there must be some kind of force between those liquid molecules that allows them to keep on touching each other. And that's the nature of what we're looking at here, where there's three intermolecular forces we're going to talk about. The first one is the weakest one, that's the van der Waals force. The second one is called dipole dipole, and the third one is called hydrogen bonding. So they're incrementally larger in strength. The van der Waals are weakest. The dipole dipole is 10 times stronger, and the hydrogen bonding is 10 times as strong as a dipole dipole. So these are the forces that are indeed keeping these things together. So what I'm going to do is I'm going to open up my video here to show you this. So this is a good video to watch. And it's the Intermolecular Forces main concepts video, yeah. Let's see if I can get. Okay, so this is the same thing as what I've got on the screen here. So this is van der Waals, or also called London dispersion forces. Now, what I want you to imagine is that if we're dealing with just C's natures, and that's all we're looking at here, C's natures, you imagine that there's an electron cloud that results from the electrons in the CH bonds all around the CC chain here. And what can happen is that this electron cloud here can become distorted one way or the other. But what's important to note is that distortion is only temporary. So I'm going to show you a picture of what that looks like. It's a really nice interpretation of van. So you can see there it is there. So you can see the electrons moving from one side to the other. It's a very temporary type situation. That makes this a very weak kind of intermolecular force. So what happens is that when we're looking at the distortion of that cloud, we can imagine a situation where we have more electrons on one side than the other. And what that means is that we're going to have a delta plus at one end and a delta minus at the other. You remember that that's got to do with partial charges. So more electrons on one side, delta minus, less electrons, delta plus. And then we've got this interaction, this electrostatic interaction that can occur in an attraction between a delta minus and delta plus. And this is what keeps the molecules at least sticking together in at least weakly, and in a weak fashion. And that's because this is a very temporary type situation that we're dealing with here. Does anybody have any questions about van der Waals forces? The stronger force, next one, is the intermolecular force called dipole dipole. It's 10 times as strong as van der Waals. And the kinds of molecules that have dipole dipole forces are what I'm calling CX molecules, where C is connected to an electronegative element like nitrogen, oxygen, sulfur, or a halogen. And this results in what we call a permanent dipole, because now we've got a C bonded to F, say, and that means we've got a delta plus on C and a delta minus on the F. We've seen this delta plus, delta minus notation before when we've been talking about bond types. We saw way back in test 1 we saw this. And this is, because it's a permanent dipole, the previous one was temporary, if you'll remember. This is permanent. Let me show you, see if I can pull up the video with that part of it. Oh, somebody's got a question for me, I didn't see it. Okay, thank you. Sorry about that. Just waiting for that to disappear so I can access the link. Here we go. All right, so this is what's happened. We've got a permanent dipole, and we've got just the positives and negatives all lining up together to give us this situation where we've got a much stronger interaction between the molecules because we're dealing with a permanent dipole as opposed to a temporary one. So it's 10 times stronger, excuse me. That's 10 times stronger than the van der Waals that we just looked at earlier. Does anybody have any questions? So again, just summarizing so far, van der Waals is all about C's natures. If you throw in a bond to something electronegative, then we're subject to dipole-dipole forces. And there's one other special dipole-dipole force I want to talk about that's called the hydrogen bond. And this is specific to a situation where we've got OH, NH, or FH. And the reason for this is because hydrogen is a much smaller atom than any of the other atoms that we really talk about. So when we're looking at an OH bond specifically, O is a pretty big bond. Hydrogen is pretty tiny. So we've got a bond between the O and the H. And what that means is this distance here, because the hydrogen's small, we've got a fairly small distance between this delta minus and delta plus. And because we've got that small distance between this delta plus and delta minus, that means that this interaction is going to be a lot stronger than it would be if this wasn't hydrogen. So that's the big difference here with the hydrogen bonding. So it's kind of like a special case, really, because it only deals with OH, NH, and FH. And O, N, and F happen to be the 3 most electronegative atoms on the periodic table. So when you've got that combined with this small hydrogen atom, then we get this very interesting hydrogen bonding case. All right, let me show you something here. I'm going to have to pull up another site. I think I can't remember if it's, I think it might be in my video, but I'm going to pull this up anyway. Mission states. Intermolecular forces. See if I can pull up. It's not what I was looking for. This one here. No, there's not it either. I'll get there in a second. Oh, there we go. That's what I'm looking for. Okay. No. All right. See if I've got it on the video here. No. Okay. Sorry about that. I'm finding it difficult to access the links I need to because I'm not accessing this from the same place as I used to. All right. Yeah. No, I'm not going to worry about it. All right. Let me talk about the other things. I was going to give you a bit more context for that, but I can't access the website I need to here. I can't spend time looking for it. The other things that are going to influence intermolecular forces are what I'm calling chain length and branching. So with chain length, this will make some sense, is that we've got long chain versus short chain. And with long chain, you're going to be able to have more surface contact between the molecules than with short chain. So what we find is that we've got more surface contact with this long chain than the short chain. We can also say the same thing about straight chain versus branch chain. Now, straight chain, you can see it's very, very flat, looks like cigars in a box. Whereas once we put C's off the chain, it's kind of like spheres in a box. And spheres in a box always have less contact between them than cigars in a box will. So that's what's happening there. Does anybody have any questions about that? So what we're going to do here is we're going to take these intermolecular forces, we're going to relate them back to boiling point. So you remember I showed you that diagram with the liquid turning into the gas, how the liquids were molecules that were touching, and then gas molecules weren't touching. So that's the point I'm trying to make here. The boiling point is the temperature required to turn liquid into a gas. That is the temperature required to make it so that those molecules don't touch anymore. It's the intermolecular forces that keep the molecules touching. The stronger the intermolecular force, the higher the boiling point. So that's the main thing I want you to understand here. Does anybody have any questions about that? Yeah, so this is the site. These are the sites here. You can actually access them on the PowerPoint on your own if you want to. I just can't pull up the PowerPoint here properly. All right, so let's look at the examples that you need to be aware of here about how to determine the differences between the intermolecular forces. All right, so this is kind of like a little, I don't really want to call it a cheat sheet, but it's kind of like a summary, I guess, of what we've just been talking about. So we've got Van der Waal, and that is CH only. And these forces are less than dipole dipole, which is CX. And then you've got that's less than hydrogen bonding, which is OH, NH, and FH specifically. So that's it. That's what we need to be aware of. Let's go take a look at the test, and you'll be able to see how we can use that information. We can use that information to solve problems that relate to this. Intermolecular forces. Here we go. All right, so it's asking here which compound has the higher boiling point. So when you're looking at this, I want you to remember what I had told you earlier. When you've just got this kind of situation which is just lines, then you can assume that's all CH. So what I would do there is I'd immediately be aware that the first one is van der Waals. And down here, I'm looking for the strongest force, and I can see I have an NH there, and that would indicate that I have hydrogen bonding. So I had told you that this is the hierarchy, is the strength of these intermolecular forces. So the one with the highest boiling point would be the hydrogen bonding. So that would be the answer there. All right, I want to make sure everybody understands exactly what I'm talking about here. Does anybody have any questions? So what do you have to be able to do? Well, you have to be able to look at these diagrams and tell which intermolecular force you're dealing with. You also have to be able to identify the different things that help you to figure out what the intermolecular force is. Anybody have any questions? Okay. Which compound has the lower boiling point? Okay, can anybody tell me what the intermolecular force is for this one? Anybody want to say? If nobody's saying anything, I'm going to assume that you have no freaking idea what I'm talking about. Or nobody does. Is that the assumption I'm supposed to make here? Nobody has any clue? I'm not getting any answers here. I'm not even sure you can hear me. I'm not even sure anybody's listening to me.
Would it be O?
Well, which intermolecular force is it? Is it van der Waals, dipole dipole, or hydrogen?
Would it be van der Waals?
Well, I see an O in there, so it's not all CHs, right? Right, so it's not all C, so it can't be van der Waals.
So it would be the last one.
Well, that requires OH, NH, and FH. This O doesn't have an H on it, does it?
Okay, so it has to have a H attached to it for
Yes.
it to be considered. So like the
Absolutely.
one beneath it would be considered the third one.
Yes, yeah, I appreciate you saying that, Richard. Yes, that's true. So
Okay.
what's that leave the other one?
The last one.
DD, right? So dipole dipole for the top one, and then just as you said, hydrogen bonding on the bottom one. And that's because it's got the NH in it. That makes it hydrogen bonding. The other one's dipole dipole because it's not, well, it doesn't have anything, it doesn't have an OH, and it's not all C's and H's. So which one has the lower boiling point of those two? Well, it's going to be the dipole dipole. Does anybody have any questions? I don't know, it's like pulling blood from a stone, getting anything out of you guys. I tell you what, in the future, if this is going to be in the spring, I'm going to make people turn on their video. I can't do it this semester because I didn't put it in the syllabus, but the lack of interaction is just astounding. You know,
The reason I think I thought it was VDW was I saw the O and I thought it was O only. I mixed it up there.
Right.
Beneath the CH, I thought it said O only, but it says only.
Oh.
On the right hand side, where you have it written out, I just thought it said O only, and
okay.
it says only. Yeah.
I see. Okay.
So that's why I thought it was VDW.
Right. Okay. All right. Does anybody have any questions? Look, I'm not here for me. I'm here for you all. That's the thing. I don't know. I don't know what the heck's going on. All right. Let's talk about solubility then. Well, does anybody have any questions? Honestly, come on, please. I don't think it's that hard.
I'm a little bit lost with number 22.
Okay.
In fact, very lost. So we're looking for the lower boiling point, and we can tell the lower boiling point. The only clues they give us is that it's got an O for one of the hexagons and an H for the other one. Now, how do we link that back to that chart that you made at the top? I don't get that chart.
Well, look, if it was just C's and H's, it would look like this, David. Right? It would have just been dots and lines. That's it. Right?
Okay.
That's all. That would be CH only. That would be van der Waal. You with me?
Yeah.
Remember, each of these represents a C. Okay? Every one of those represents a C. So DD would be CX. That's when you got C connected to X is electronegative, by the way. It's anything electronegative, non-metal. And you can see this does have CX bonds in it, CO, right? It's got CO bonds. You'll notice there's no OH, NH, or FH in that top diagram. Are you with me on that?
Yeah. There's no OH, NH, FH in the top
Yeah,
one.
so do you see even just by process of elimination, you can figure out that it's dipole-dipole.
And how does that link back to the boiling point?
Well, it's the intermolecular force and the boiling point are linked. The weaker the intermolecular force, the lower the boiling point.
So you're saying the weaker is the X the molecular force? Is that what it is?
No, the intermolecular force is this, the van der Waal, dipole-dipole, hydrogen bonding.
Okay. All right.
And the greater than or less than signs we've got here explain the magnitude of those forces relative to each other. And it's the same thing for boiling point. So van der Waal is the weakest of all the forces. So those are the ones that have the lowest boiling point.
Okay.
I'm not sure, is there anything else I can say to help clarify that?
No, I don't know, I just need to rewatch this lecture.
No.
Probably a few videos too. A little bit
All right.
lost, that's all.
Okay. I don't know what else I can say to make it clearer.
No, it's fine. It's fine.
Does anybody have any questions? Or is everybody feeling like David? Is anybody even listening aside from David and
So
Richard?
basically just the DW, if like there was an example, it would just be completely blank. It wouldn't have anything like O or NH on it.
No, it would just be that. Yeah, it'd just be these lines like I've got here.
Okay.
Yeah, like that or like this. Yeah, but these are all examples of VDW. And anything like that would all be van der Waal. And then once you throw in something like X, where X is O or CL or F or anything, then you talk about dipole-dipole. Then if you have OH, NH, or FH, we're talking about hydrogen bonding.
So if it's just like a single O, it would be DD, but if it's like NH, it would be HB bonds.
Right. Or if it was OH, right? Just say it was OH, that would be hydrogen
HB.
bonding. Yeah. That's what I want you to. That's all I want you to be able to do. Just look at those and be able to identify what the intermolecular force is, and then also appreciate what the relative magnitude of those forces is, and how that relates to boiling point. Yeah. All right. We can also talk about how that relates to solubility. So we know that like dissolves like. So the most popular hydrogen bonding solvent that I can tell you about is, of course, water, because that's all OHs. And if you're talking about a hydrogen bonding solvent, now remember when we talk about solvents and solutes and such, a solvent is doing the dissolving. And it turns out that hydrogen bonding solvents like water will tend to dissolve hydrogen bonding solutes. You know, things that you add to it. I'll give you an example. If you were to take sugar which has lots of OHs in it, it dissolves pretty easily in water. But if you've got a Van der Waals solvent, then it tends not to dissolve those things. And a classic example is oil and water. So if you've got water and you put oil on it, you know the oil's going to float. The oil is all hydrocarbon; it's all carbon and hydrogen. So it doesn't dissolve at all. However, if anybody's ever used a two-stroke engine, you know you have to use a mixture of oil and gasoline. Those two things are soluble in each other because they're both Van der Waals. So we know how that goes. So let's see how we apply that. Down here. It says here, which compound has the highest solubility in C6H14? Well, the first thing you need to do is look at C6H14 and say, well, what's the intermolecular force with that? Anybody know? What's the intermolecular force involved?
VDW.
How do you know that, Richard?
Because it has CNH in it.
And only CNH, right?
Yeah.
Yeah, good, thank you. That's great. Now, we're asked which one has the highest solubility. So you look at the OH one here, and that's going to be hydrogen bonding because it's got the OH. The other one is dipole dipole. And if you look at the diagram I've got back over here, we've got a Van der Waals solvent. The highest solubility would be Van der Waals, followed by dipole dipole, followed by hydrogen bonding. So out of these two, the one that would be most like would be the dipole dipole. The one that's least compatible would be hydrogen bonding. So this is all from like dissolves like. Does anybody have any questions?
That's not going to be on the test, right? That chart right there. We're going to have to memorize that.
Memorize. That's a bit. I don't know. I don't feel like it's really memorization, Kendall.
Okay.
Because it's a matter of understanding compatibility and like dissolves like.
Okay.
But to answer your question, no, you won't have it. That's right. All right, any other questions? Okay, we'll leave it there for today. And I'll catch up with you all on Wednesday. All right, thank you.
Thank you.
Have a good day.
You too. Thomas, can I help you?